right, so did you come up with a reason for why the cans that we drink, Coke and Sprite and Mellow Yellow and whatever else, Dr. Pepper, why those are not in the configuration that we came up with down here, which is basically the profile is what? A square, we said, right? Diameter is 3 inches, height is 3 inches. And when we look at cans of Coke or Sprite, they are not in that shape. Why is Coke spending more money on the surface area? Right? They're not minimizing the surface area, obviously, because we've solved this problem. Well, hopefully you came up with some possibilities. Obviously, you know, we made some simplifications, assuming it's a perfect right circular cylinder, which is not necessarily the case. And so there could be some difference there. Also, you know, there's more to design than just the pure minimization of the surface area. Some of you might have said, well, you know, it wouldn't fit right in the hand, or, you know, we would sometimes talk about ergonomic design, right, making sure it's useful for people to handle. I mean, you can imagine if the dimensions to minimize the surface area where R was really big. I mean, you can have you know, you won't want to be drinking out of a can of tuna fish, you know, that sort of shape, you know, it'd be really difficult to drink. Or the other extreme, right, where you're trying to drink out of a long, small circular tube almost. But here's probably another possibility, and I don't know the answer. I'm not saying that I know why these bottling companies bottle in the way they do. Could also have to do with packaging and shipping and other things, just the ease of the equipment that assemble these things. But when I look at a can, one of the things I notice is that the sides, the material, the aluminum on the sides, is much thinner than on, say, the top or the bottom, maybe. The top, you know, has to have the seal put on it, you know, and the cap and everything, the pull tab or whatever. So there's obviously some cost associated with that too. So what I thought of is, hey, maybe it is that the sides material is thinner, so maybe it costs less than the cost for the top and bottom. And so here is my modification of the problem, because really minimizing surface area doesn't necessarily minimize cost if the costs indeed are different for the different materials. So if the aluminum of the sides of such a can of soda cost 1 cent per square inch, and the top and bottom cost 2 cents per square inches, what dimensions of the can will minimize the cost to make the can? And, you know, so we have the same can that we had before. We'll draw a picture of it, right? And we have the same dimensions. This was the radius here, and this was the height. That doesn't change. But notice we're minimizing now what? The cost, not the surface area. Okay? So if we let C equal the cost, right, then what is the cost? Okay? Well, I'm going to do the cost, and I'm going to do this in cents. You know the sign for cents? That sign right there? Cents. Pennies, right? Cents in pennies. You could do it in dollars. The reason I'm going to do it in cents, instead of having 0.01 per square inch here, I'll just have what? 1 per square inch. And instead of 0.02 per square inch, I'll just have 2 per square inch. So what is the cost? Well, the top and bottom cost 2 pennies, 2 cents per square inch. How many square inches for the top and bottom? Well, that's surface area. The top and bottom, we said what? 2 pi r squared. That's the area for the top and bottom. But I want the cost. What's the cost? It's 2 cents per square inches, right? This is the area, top and bottom in square inches, right? And then I'm going to multiply it by 2, and this is what? Cents per square inches. So when I multiply, I get cents, right? This is how much in pennies, right? This side of the top and bottom of the can will cost. Plus I got to do the cost for the sides. Now the sides, 2 pi RH, right? Remember that was the area of the sides. Go back in the previous video and see how we got that, the sides. But what's the cost for the sides? It's 1 penny, right? So just 1 penny times 1, right? And so this is the cost, and if I simplify this out, multiplying by 2, I get 4 pi r squared plus 2 pi rh. This is the very same equation we just did in the last problem. The only change is the 4. There was a 2 here, and now it's a 4. Everything else is the same. Everything else is the same. In fact, the constraint was the same. What was the constraint? It was still the volume, right? It's a 12-ounce soda can, and if you remember, we were going to use cubic inches, and so that's about 22 cubic inches from the last problem. We're going to use that quantity. So the volume constraint was what? Pi r squared h, that's the volume, is 22. This is the same as we had in the last problem, right? And I solved for h, 22 over pi r squared, 22, why did I write 2 pi? 22 over pi r squared, right? And that quantity we're now going to plug in here. Right? And so what does my cost become? H is 22 over pi r squared. And this is exactly the same as it was in the last problem over here. The pi's cancel. One of these r's cancel. And what do I have? Cost is 4 pi r squared plus 2 times 22, 44 over r. And remember, this was valid for any value of r greater than 0. It's the same thing here, right? We talked about that dimension. And so we have an unbounded open interval, no endpoints. And so what are we going to do? We're going to find the derivative, right? Very similar to what we did before. Derivative here is what r squared is 2r, so 4 pi times 2 is 8 pi r. And then the derivative of this, remember, 44 times r to the negative 1 is negative 44 r to the negative 2. Right? And let's write this as one fraction, common denominator of r squared. So it's 8 pi r cubed minus 44 over r squared. Okay. So just again, combining this as one fraction. And then we know that the derivative here, the cost with respect to the radius is 0 whenever the numerator is 0. Okay. And that's going to be, if I solve for r cubed, I will get r cubed equal to 44 divided by 8 pi, right? Add 44 and divide by 8 pi, which if I divide top and bottom by 4 is 11 over 2 pi. And so you might think, remember when we did it last time, it was r cubed was 11 over pi. Now it's 11 over 2 pi. So r is now the cube root of 11 over 2 pi, which is about, use your calculator, 1.2 inches. Check and verify that, 1.2 inches. Now, we still need to do a sign check, and it's going to be very similar. Remember, or our derivative, because I have an open, unbounded interval, and we're talking about for all values greater than 0. Now our critical point's at about 1.2 inches. And so the sign is 0 there. If I plug in something less than 1.2, like 1 up here for r, get 1 in the denominator, 8 pi minus 44. Pi is 3.14. 8 times 3.14 is about 25, 26 maybe max, but it's certainly less than 44. So the difference is negative. For values are greater than 1.2, like 1,000, right? Then this 8 pi r cubed is much, much bigger than 44, and the difference is positive. Denominator always is positive. So we certainly have a minimum. So the right, because the sign changed from negative to positive tells me we have a minimum. Exclamation point there, minimum, yay. So the cost is minimized, in this case, minimized, when our radius of the can is 1.2 inches, and what's our height of the can in that case? Well, if you go back and plug this value in 1.2 inches into this formula, and do it like I did in the calculator, that's 22 again, you know, without rounding, using the answer key, and you will get about 4.8 inches. Now, so now the profile is what the radius is 1.2 inches, so the diameter is 2.4 inches, and the height is 4.8 inches. So now the height is about twice the diameter of the can. And that is a little bit closer to what we normally see for a can of soda, for instance. Okay, so I have no idea. I just made this up. I have no idea, the amounts of the costs for the two, basically saying the cost of the sides is twice the cost of the top and bottom, changes the dimensions this way. And I have no idea if that's accurate or if that's even the cause for the shape of the can or part of it. But just a thing to think about in this problem. And this is an important area with multi-billion-dollar industry, the packaging industry, right? I mean, if you go in a store, what do you see? What do you see in the shelves? You see packages. Everything's in a package. A can, a box, some container. And so being able to there's a lot of money in that, being able to design these packages to minimize the material, to save cost, but also to be able to do what it was designed to do, to hold and be easy to transport, etc., etc. Okay, let's take a look at one more problem here. In this problem, a little different. We're going to do a little gardening. Well, actually, we're going to help design a garden. A gardener wants to enclose a rectangular garden on one side by a low brick wall that costs $25 per linear foot, and on the 3 remaining sides by a metal fence that costs $10 per linear foot. If the garden is to enclose 50,000 square feet, what dimensions will minimize the cost? Well, it sounds familiar to what we just did. We did a minimize the cost problem. So we're going to do the same thing. Let's just go ahead right away and let's say let C equal the cost, right? We need to assign variables to this. So how much does it cost, right? Well, again, this is kind of like the corral problem in the sense that we're doing a rectangular garden. So let me draw that rectangular garden from high above. It would look like a rectangle. And we do have one adjustment though. I can label this X and this Y, like we did with the corral problem, right? Length and width, whatever variables you want to. You should assign them though. Make sure you clearly label that. But what's important about this is what we need to know: what side has the low brick wall, right? One side by a low brick wall. So you need to identify which side it is, okay? And just I have no idea. The way I've got it drawn, it looks like Y is smaller than X. Doesn't have to be. But I'm thinking, to minimize cost, the brick wall costs a lot more per linear foot than the metal fence. So I'm going to let one of these sides, I'm going to let this side be the brick wall. I'll just indicate that with a bigger, no, just even indicate here's our brick wall. So you need to indicate that, right? It depends. I mean, so, you could draw this problem where your brick wall is down here. That's fine. Then the brick wall is what length? X. The way I have it, what's brick wall length? Y. That's important. Okay? So from this, what is our cost? Cost is the amount for the brick wall, right? The brick wall costs $25 per linear foot. So how many feet of brick wall do we have? How many feet? We have Y feet, right? Y is the dimension of the brick wall's length. So Y feet. So what's the cost? $25 per linear foot times the number of feet. That's the cost in dollars, right? It's the cost in dollars. Remember, our cost here is in dollars. Okay? So this is the cost for the brick wall. And then we're going to add to that what the cost for the metal fence. Now the metal fence costs $10 per linear foot, and I need to know what is the amount of the length of the metal fence I need. So metal fence is all the remaining 3 sides. So how much do I have? I have X feet plus Y feet plus X feet. X plus X is 2X plus Y. So I'm going to put in parentheses here 2X plus Y. That's the length of the metal fence. And so this is the cost for the metal fence. Okay? So if we're given the value of x and y, I can compute the cost. But my question is, what values of x and y will make this cost as small as possible? Let's get the best we can do cost-wise. All right, let's clean this up over here a little bit on this side. By distributing that 10, I get 20x plus 10y. Combine like terms, 25y plus 10y, 35y plus 20x. Okay. Now, what do we have? We have cost as a function of how many variables? Cost is a function of two variables, x and y. What do we want cost as a function of? One variable. All right. Where's our constraint in this problem? What's our constraint here? The area enclosed, right? 50,000 square feet is the area enclosed. And so therefore we have an area constraint. All right, 50,000 square feet. And so what is the area of our interior region of our garden? What's the area of the actual garden? Well, it's length times width. It's going to be x times y. So x times y is the total 50,000 square feet. So there's the relationship. I want to solve for one of my variables here. I'm going to solve for y by simply what? Dividing by x. Now, what are the possible values for x? X is the length of this wall. So x has to be a positive number. Could x be 0 in this problem, like it could for the corral problem, when we were enclosing the maximum area for the rancher in the first problem? Answer: no, because see right here. Notice that x times y has to be 50,000. If x went to 0, the enclosed area would be 0. So no, not in this case. And so x is just any positive number. Actually, there's no upper bound for x either. The bigger x is, the smaller y is. Okay. And so this is the constraint. I can now plug this value in y. And what do we get? We get the cost is, let me put this 20x first. Can I do that? 20x first, and then 35y plus 35y is 50,000 over x. Right. And let's clean this up a little bit. 35 times 50,000, that's a pretty big number. It's actually 1,750,000 over x. And so there it is. Here's the function. Here's the function I want to minimize on this interval. Notice this interval is unbounded and open, so we're going to be doing the first derivative test. So we need the derivative of this function with respect to x. Derivative of 20x is easy, that's 20. And what's the derivative of this? This is 1,750,000 times x to the negative 1 power. So the derivative is what? Negative 1,750,000 x to the negative 2, or minus 1,750,000 divided by x squared. Okay. So I can find a common denominator like I did before, but let me just say that this derivative is equal to 0 whenever what? Whenever 1,750,000 divided by x squared equals 20, right? When this thing here is 20, 20 minus 20 is 0, right? So this is the case. Multiply both sides by x squared. Divide both sides by 20. And I get x squared is equal to 87,500 if you divide that by 20. And so x is the square root of 87,500. Now I could simplify that, but it's not a rational number. And you would not want to go to the store and say, yes, I'd like the square root of 87,500 feet of fencing. So we're going to approximate this, and this is about 296 feet. 296 feet. All right. So are we done? Do we just say there's the dimension that will minimize this function? No. The derivative being equal to 0 could be a minimum, could be not a minimum, it could be a maximum. And you would be fired if you were on this design team and you designed it so that you maximized the cost, right? You don't want to do that. And so we want to make sure that this is indeed a minimum, and we do that with a sign check of our derivative. And so remember, the interval we're talking about was only greater than 0. Here about 296 feet is about where our derivative was 0, right? And then plug in a number less than 296 feet into our derivative. Here's our derivative right here. If I let x be what? Between 0 and 296, let x be 1. 1 foot. 1 foot and all. So 1 squared is 1. I just get 20 minus 1,750,000. That's a big negative. Something bigger than 296. Well, notice anything bigger than 296 is going to make x squared. I lost my. Oh, it was going to make this ratio here bigger than. Sorry, smaller than 20. I'll get it straight. All right, so anything bigger than 296,000, then this ratio here is going to be smaller than 20 because x squared. Well, just choose x to be something really big, like a billion, right? 1 million divided by a billion is less than 1, for instance, and so 20 minus something less than 1 is positive. Okay. Again, you can just plug in and get these signs. But again, what do we have? Sign changing the derivative from negative to positive. That means we have a minimum at that location. So the cost, so again, we have a minimum. And it's the only local extreme value, so we're going to go down and then back up for the cost. So that is the absolute minimum for the cost. So the cost is minimized when the dimensions are x equal to 296 feet and y. What's y going to be? Well, how do I find y? Well, y, if you remember, was 50,000 divided by x, right? So let's just go through this again and just show you how I would do this in the calculator. I would take, first of all, to find x, the square root of 87,500. Right, there's my 296 about, rounding off to the nearest foot. Keeping that in there in my calculator, then I can divide that into 50,000 to get y. And I'll just do divided by answer, right? That will be without rounding. So it's about 169 feet for y. Feet. And again, that was the 50,000 divided by this. So there it is, right? And if you go back to the picture, then the brick wall was length y, so 169 feet, that's how much length of brick wall we're going to have. The metal fencing then will be these lengths and this length, right? So this length here was the 296 feet. Okay. So an interesting thing, you might have said, well, you know, the cost of the brick is so much more, so make that as small as possible. You have a very narrow, long garden. But what happens is as this y value gets smaller and smaller, even though the brick wall costs more per linear foot, as y gets smaller and smaller, the length of the metal fencing, the x values get so long, right? The length gets so much that even though it's $10 per linear foot, if you make y too small, then the cost begins to go back up again. And so this is the equilibrium point, so to speak, the point where the cost is minimized. So there's your answer. Now, what would the cost be for this whole construction? Now you can take these values of x and y and you can plug them back into our original cost function right up here if you want to, for instance, and you can find the estimate for the cost in dollars. All right? And so this is a very practical problem. I mean, simple, and you can think about how you can use this in designing all sorts of things, right? How I can minimize the cost, for instance, or maximize the enclosed area, minimize surface areas of different shapes. So very powerful, very neat application of derivatives. Okay. In the next video, we're going to look at one more problem, a little bit more abstract problem, a little bit different, but still using the principles of optimization.